discussion on assignment problem. And you know that in the last class, I told you about the mathematical model of assignment problem, which is actually a special case of linear programming problem. And also, assignment problem is a minimization type of linear programming problem. So the points which we learned in our last class, let us jot down all the points together. Point number one is okay, was assignment problem is a special case of LPP. Number two, you want to say something, Spandan? You can unmute yourself and then can say. Assignment problem is a special case of linear programming problem. Assignment problem is a minimization type of problem. Okay, and also I discussed about the Hungarian method, which is often used to optimize the assignment or to find the solution, optimum solution of the assignment problem. Now, one more thing I would like to add to this particular points is that, as I told you, that linear programming problem is a kind of problem where the feasible solutions can be anything, any real number. But assignment problem, the variables, that means xij's, are obtained when you assign a particular person to a particular job. So the possible values for xij's are either 1 or 0. If I is assigned to j or j is assigned to I, and this is the case when I is not assigned to j or j is not assigned to I. And since this is one of the most fundamental difference between assignment problem and linear programming problem, this is the special, therefore assignment problem is called a special case, because it can take any two values, either 1 or 0. Okay, but linear programming, in general linear programming problem, the variables can take any value, any real number. So sometimes assignment problem are also known as integer linear programming problem. Integer linear programming problem. Integer linear programming problem. Okay, so because the values which the variables are taking, they are integers. Specifically, they are integers, either 1 or 0. But in linear programming problem, you can have fractional values also. Although linear programming problem, we have sometimes we have counted numbers, how many variables, how many items to be purchased, or that kind of thing. Apart from this, there are some other situations where you can have fractional values. Right now, I cannot give you example of that because I do not have one with me. But if we get an example, if I get an example later, I will share with you. But remember this point number 3. So assignment problem is also sometimes known as integer linear programming problem. As I told you, today I'm going to discuss further on Hungarian method. The last class discussion was not complete because we reached a solution very easily after 3 steps. But I told you that there may be situations where after the 3 steps you may not get the solution, and we have to do something else with the method. So there are some other points in the Hungarian method which need to be applied when after applying step 3 the optimum solution is not reached. So today I'm going to explain that first of all, for which I'm going to take an example. We are to find, okay, I'm copying it from my one of my PDF file. I'm not sharing the PDF file with you because in that case I have to stop sharing the whiteboard. So the matrix goes like this. So we are to find the assignment, the optimal assignments, where the matrix is given as follows. We have 4 jobs. We have 4 jobs and 4 persons. And the values, the cost, it is a cost matrix. So values are given as follows. $1, $4, 6, and 3. Next we have okay, this is the cost matrix which we have, and I am writing the dollars just to let you know that it is a cost matrix. But you know that the units, the which are actually all the elements of the assignment matrix must have the same unit. You cannot have a mixture of elements, like some elements of the matrix is cost and some elements of the matrix is profit. This cannot be like that. So, and also I told you one point that Hungarian method is only applicable to the problem where the problem is of minimization type. So first of all, we have to make sure that the problem is actually a minimization type of problem. Otherwise, if the problem is maximization type, Hungarian method is not directly applied. Though what sort of things can we minimize? We can minimize things like cost, we can minimize things like time, distance, etc. And so first of all, we have to be told that we are given this kind of elements in the problem. And also I told you that the exam question setters in the examination are not in the habit of letting students know what sort of matrix they are giving. They just think, by convention, students understand that if nothing is mentioned, it is a minimization type of matrix. So therefore, I am specifically letting you know that it is a cost matrix I am taking. So Hungarian method will be directly applied. From the next operation onwards, I will not write the dollar signs. Okay, so you can avoid writing these dollar signs, or you can keep it. Doesn't have anything to do with Hungarian method because the methodology will not change in this regard. The first 3 steps of Hungarian method, step 1, step 2, step 3, if you have these steps with you and if you have copied it earlier, so in these steps, the row operations, the column operations, and the assignments were discussed, which I'm going to apply. I'm not going to write the steps. Okay, I'm just going to apply these steps in the given matrix. So first of all, okay, so we have this matrix, and you see the row operation tells us that I told you to write row operation over here. Okay, so row operation tells us that you have to select the first row, identify the minimum element, and subtract this minimum element from all the other elements of this row, including itself. Let us first identify all the minimum elements. So minimum element in the first row is $1. Minimum element in the second row is $7. Minimum element in the third row is $4. Minimum element of the fourth row is $5. Okay, so I'm going to apply the row operation. So you see, okay, let us write dollar sign. Let us keep the dollar sign. So it is $0, it is $3, it is $2, and this is, oh sorry, not $2, $5, and this is $2. Now next comes this one, 2, 0, 3, and 2. Next comes this one, third row. So we have okay, so we have got our first matrix after putting the row operations. So you just recheck the calculation. If I do anything wrong, you let me know by writing in the chat box. Now I'm going to apply column operation. Column operation, which will be applied not on the original matrix, but on the resultant matrix, which is obtained after row operation. Okay, so this is, sorry, let me write it clearly. Okay, now we are going to write the, we are going to mark the minimum elements in the second matrix, because we are going to study them column wise now. So in this column, you see in the first column, the minimum element is 0. See, so you can mark either this minimum element or that minimum element, doesn't matter. So I'm marking this. In column 2, I'm marking this minimum element because it is the minimum element. In column 3, there are two minimum elements, 3 and 3. You can mark any one of these two. I'm marking this one. And in 4, we have got this minimum element. So now we are going to apply the same thing which we did for row operation with respect to the columns. And consequently, we get, as you can see, the first column will not change because the minimum element is 0 here. The second column will not change because the minimum element is 0. Third column will change. This will become 2, this will become 0, this will become 4, and this will become 0. And the last one will also not change because the minimum element is 0. Okay, now we are going to apply the step number 3 over here to get the assignment. Apply step 3. Okay, so let us see what we get. Now, as you can recall, in step number 3, As you can recall, in step number 3, we told that first of all we have to look for a row which contains a single zero, and you have to assign it by putting it inside the box. Now if this zero is assigned, then you have to consider the column and the row which contains the boxed zero, and in that column or in that row, if there are any other zeros, you have to cross it out. So you see, in the first row we have got a single zero, so we are assigning it. Okay, now in this boxed zero is contained in this column, and in this column we have a zero, extra zero present here, so we have to strike it out. Why is it so? Because in a particular row or in a particular column, you can have only one zero, one assignment, not more than that. Now come to the next. In row 2, you can see there are two zeros. But as I told you that you have to look for a row or a column which contains a single zero, so we shall keep the row 2 for the time being. Come to row 3. Row 3 doesn't have zero at all. The zero which it had already been striked out. Now come to row 4. Row 4 contains two zeros. Okay, and therefore you cannot assign any zero. If we look from the perspective of the row, now we shall change our perspective. We shall look it from the perspective of columns. Now here you see, in the second column, there is one row. Okay, there is one zero present over here, so we are going to assign it. Now do not think, when you will explain someone about this assignment process, then you have to take care of this situation, that he may ask you that ultimately you are going to assign this boxed zero, so why didn't you do it before? You have to tell him that you can do certain things, but the perspective of doing that thing is very important. You don't think, as I'm assigning this zero, don't think that I'm doing it row wise. I'm doing it column wise. I'm seeing the column, and I have found that in this column only one zero is present, and therefore I'm assigning it. Previously I was seeing it from rows perspective, and I found two rows over there, so I didn't assign it. Now as this has been assigned, this boxed zero is contained in this column and in this row. Okay, this boxed zero is contained in this column and this row, and in this row there is one extra zero which will be striked out. Then you come to next column, that is column 3. In column 3, you can find that there is one zero present, so we will assign it. And in this assigned zero of column 3 is contained in this column and was contained in this row, and in this row we have another zero which will be striked out. So in this way, all the zeros present and all the zeros present in the third matrix have either been assigned or have been striked out. Okay, but here comes the most important part, and we are going to note it down. The important observation which we have made is that the requirement of assignment problem is not fulfilled. The requirement of assignment problem says that in every row and in every column there must exist one and only one assignment. But here we find that in the third row, or you can say in the fourth column, there is no assignment. In the third row or in the fourth column, there is no assignment, and therefore this assignment matrix is not an optimal matrix, so we have to do something else over here. So before I write step number 4, okay, so our conclusion is that so the third matrix is not the optimum matrix or the minimal matrix. I have used the word minimal. Remember, I shall explain why is it so. So before I write step number 4, let us copy the third matrix once again. Okay, so that will be required for our purpose. So we have 4 jobs. And what were the matrix? What matrix elements? Matrix elements were 0, 3, 2, 2. Okay. Let me copy it first. Okay. 0, 3, 2, 2. Next we have 2, 0, 0, 2. Okay. 2, 0, 0, 2. Next we have 0, 1, 4, 3. 0, 1, 4, 3. And lastly 3, 2, 0, 0. 3, 2, 0, 0. Now step number 4 goes like this. Since we have not obtained the optimum matrix, or the minimal matrix, since in every row and column there was assignment, there was no assignment, we now consider the third matrix and mark the minimum element present in the matrix. Among all the elements. If there are 2 minimums, we choose any one of these arbitrarily. Okay, so you see, look at this matrix, and in this matrix the minimum element we have now, the minimum element of all the elements. Okay, now just a minute. Okay, before that we need to do one thing. Before that we need to do one thing. Before you mark the minimum element, you have to do one thing that I had to write it before because I missed it. I'm going to write it over here. Anyways, no problem. Because you see, if since you are going to mark all the minimum elements, since you are going to mark the minimum elements from the entire matrix, now you will say that the minimum element in the entire matrix will be 0. So 0 will be marked. So it is actually not that. This minimum element which has to be marked in the entire matrix has to be a non-zero element. Now, how to find it out? Okay, I'm going to write it. So we are going to make this step as step number 5. But before that, we need to do something over here. Step number 4 will be something else. Okay. What is this? Step number 4. How many assignments have you got? How many assignments have you got in the previous matrix? The number of assignments you got in the previous matrix is 3. How many assignments you are supposed to get in the previous matrix? 4, because the size of the matrix is 4 by 4. So let us write this point first of all. The size of the order of the matrix, the order of the matrix is 4 by 4. So we are supposed to get 4 assignments in total. 4 assignments in total. But in the previous matrix, we have got only 3, which is less than 4, and therefore the solution was not optimal. Now there is a theorem which goes like this. I'm writing the theorem over here. The statement of the theorem is, in an assignment problem, the minimum number of lines which can be drawn to cover all the zeros must be equal to the number of assignments possible. Number of assignments possible. What does that mean? It means that you see in the previous matrix, there are only 3 assignments. So I have to cover this assignment by drawing certain hypothetical lines. Okay, these lines will cover all the zeros. Why should I cover all the zeros? I'm going to talk about that. But this number of ways you can cover all the zeros, that should be equal to the number of assignments which was possible in the previous case. Okay, so if I ask you to cover all the zeros, what will you do? You can cover it by drawing horizontal lines like this. You can draw a horizontal line like this. You can draw a second horizontal line and third horizontal line and a fourth horizontal line, but this will not work out, because in that case the number of horizontal lines will be 4, but which has to be 3 actually. So you have to look for 3 lines which should be drawn to cover all the zeros. Now I'm going to a little bit of inspection tells us that you can do it in the following way. You can identify which particular column or which particular row contains maximum number of zeros. So this first column contains the maximum number of 0. So you draw a line over a hypothetical line, dotted line like this. Then come to the second row. Second row contains the maximum number of zeros. So you draw a dotted line like this. And then you see in the fourth row, there is a maximum number of zeros. So this will contain a dotted line like that. So you see, by drawing these three lines, we could cover all the zeros present in the previous matrix. Why did I cover all the elements, all the zeros over there? So that I can apply step number 5. In step number 5, it is said that you have to select a minimum element from among all the elements. So I am going to modify this statement a little bit. We now consider the third matrix and mark the minimum element present in the matrix among all the uncovered elements. Because that's why I covered the zeros, because otherwise the minimum element will be selected will be 0 always. Okay, so that will be meaningless. So among all the uncovered elements, if there are 2 minimums, we choose any one of these 2 arbitrarily. Okay, let us put star to mark that uncovered element. Let us put star to mark that uncovered element. Okay, now you see 3, 2, 2, 1, 4, 3. These 6 items are the uncovered elements. So we can easily see that among these 6 elements, 1 is the minimum element. So we are going to put a star mark over there. Okay. Now step number 5 is not done. I'm not done with step number 5. So I'm going to write something else over there. But before that, let me copy the matrix in my copy, because the class timing is running out. And once this class ends, so in that case, I will lose my board work. Okay. So what else we need to write? I'm moving on to the next page. I'm moving on to the next page. So it is the continuation of step number 5. So after marking the minimum uncovered element, we are going to subtract it from all the uncovered elements. All the uncovered elements, including itself. Including itself. So what do we get from there? Let us quickly write. One thing has to be noted here. This is important. In the new matrix that I'm going to construct, the covered elements will remain same, and the covered elements which come, the covered elements which appear at the intersection point, will be changed by adding the minimum uncovered element over there to, or minimum uncovered element to it. Minimum uncovered element to it. Many things have been written. So let me explain what it is saying. Now you see in this matrix, these are the covered elements which have been marked by the hypothetical straight lines. But among these uncovered elements, there are certain elements that, such as this and this, which are covered but are appearing at the intersection point. These covered elements are not appearing at the intersection points. So what I'm going to do is that these covered elements will remain same. Apart from this intersection point, apart from those elements which are appearing at the intersection or junction point, other covered elements will remain same. Other covered elements will remain same, but the junction points will be changed by adding the minimum element 1 to them. So this will become 2 plus 1, 3, and this will become 3 plus 1, 4. And this minimum element will be subtracted from all the uncovered elements present in the matrix, including itself. So you just quickly take a snapshot of this particular page. I'm going to continue I'm going to continue this problem in the next class, because in this class I shall not be able to finish it.